So in this video we're going to be having a look at the Ionic model, a very basic introduction to it. You should really have already looked at or be able to use the Thomson Plum Pudding Model at least for the atom to be able to understand what's going on here. We'll start off by having a look at a compound that we should all be fairly familiar with, which is table salt. And it's obvious just from looking at table salt that it behaves in a different way to metal. It's not shiny and it's brittle rather than malleable, so if you try to bend it, it's going to snap. That's what brittle means. Although some react with water, metals themselves, they don't dissolve in water, and that's something that salt does do. Okay, so when we take a substance like salt and let it dissolve in water, we can get that substance back again afterwards by allowing the water to evaporate. Beautiful crystals can form in this way, and crystals are a sign that we have a regular repeating arrangement or lattice of particles. These solutions that form when we dissolve salts also have another curious property. They conduct electricity. Pure water alone does not conduct electricity, but salty water does. Something in the salt must be able to move around and carry charge, perhaps electrons. Well, if that were the case, then solid salt ought to be able to conduct electricity as well, and unfortunately it doesn't. So how can we explain that there are particles that are able to carry a charge that can only move when the substance is dissolved? Well, one way to consider is the fact that the particles themselves might be charged. When a substance is solid, the particles are fixed in position, but when it's in solution, they're free to move around through the water. If that were the case, then perhaps they would also be able to conduct electricity when molten. So here's an example of a type of experiment that you might see. We're going to heat up this sample, and the carbon sticks here that we use to connect up the circuit, they're called electrodes. Let's have a look at what happens to them after the experiment when we heat up some lead chloride. On a positive electrode we see bubbles of gas being produced, and on the negative electrode we see that molten lead has been produced. This suggests that the lead particles must have been positively charged, because they went to the negative electrode, and we already know that opposites attract in terms of charges. And the chlorine particles must have been negatively charged as well, because they went to the positive electrode. So we call these negative particles chloride ions, and the positive particles lead ions. The lead ions must be like the metal ions we met when thinking about metallic bonding. They don't have the same amount of positive and negative charge. This time, the electrons cannot be delocalized, otherwise the solid would conduct. There can't be any electrons occupying the spaces between the particles. They must be localized to individual particles. This leaves us with some positive ions and some negative ions. We can think of them as hard spheres, again like our basic particle model, but they won't be randomly arranged. Let's do a few thought experiments. If we imagine we have some particles arranged in a very low pressure gas, separated very far apart and moving too fast to stick to each other, and then we start to cool that gas so that if particles get close enough they have a chance to stick together, what happens next? Let's pick one positive ion and imagine it's been pinned down. If another positive ion comes near, it will simply repel away. They won't want to be near each other. But if a negative ion comes by, it will stick to the positive ion somewhere. If the next particle is a positive ion, it will want to stick to the negative ion, whilst keeping as far away as possible from the positive ion, and the opposite will be true if it's a negative ion. As this continues, you might expect to begin a line, but of course there are other places that the ions can pack. They want to get as close as possible to as many ions as the opposite charge as possible, whilst at the same time remaining as far away as they can do from the ions of the same charge. And of course this has a three-dimensional structure as well, it's not just going along in a line. We can see the same thing happening in this model of a solution that's evaporating. We write the formula of this substance as NaCl. Not because there's only one Na and one Cl in each unit, but because that's the simplest way to write it. The alternative would be to give each grain of salt a different formula to account for the fact that there are slightly different numbers of ions in each grain. That would be ridiculous, so we choose to write the formula as an empirical formula, the simplest whole number ratio in which the ions combine within the substance. And of course, in this case, that's a 1-to-1 ratio. Hence we write NaCl. I've given some simple examples here, but one individual grain of salt, of course, would have way more particles than you could even imagine. If we were able to count each particle, it would take us ages to read out its formula, and then its formula would change every time you touched it and a piece rubbed off. So remember, even if you only draw 2 ions, it's like looking through the keyhole at a much larger structure. We're not really talking about just a pair of ions. Writing NaCl has a number of problems though. Some people might mistakenly think that within the structure there are pairs which go around, and that there's something special about the bonds that joins these 2 ions, and then something not so special about the bonds joining the others. They might suggest that each sodium ion is really only bonded to one chloride ion. In reality, one sodium ion experiences an equal attraction to each of its closest chloride neighbours. There's going to be 6 of them in this diagram, but wait, hang on. Isn't it next to even more other sodium ions, which has to be repelling? Well, yes, but let's take a look at the distances involved. If we assume we have ions the same size, which is something we'll expand on a little bit later, then we'll have a perfect cubic pack. Let's scale this up to the size of meters. So for these particles that we're looking at here, we'll say that they each have a diameter of 1 meter. How close is the centre of the central ion to the centres of the surrounding negative ions? Well, 1 meter, of course. But the opposite ions, they're a little bit further away. If each of the 2 sides of the triangle are 1 meter long, then the hypotenuse must be the square root of 2, that's 1.4 meters long. So the central ion is repelled by the surrounding like ions, of the same charge that is, but they're further away than the 6 nearest neighbours, and the attraction wins out overall. If you want to think about it even more, you can imagine the next layer of ions. Each one of these will be attracted to our central ion, but a lot less. And this situation carries on. In fact, all the positive ions will attract all the negative ions within an ionic lattice, but only 6 of them will feel the strongest attraction. What happens if we start messing around with the charges of these ions? If we add 2 plus ions instead of 1 plus ions, what would that suggest about the melting and boiling points of our substances? You can imagine having ordinary magnetic spheres and swapping them for those super strong neodymium magnets at the same size. These will attract each other far more strongly and will require a lot more energy to pull apart. What would you predict, therefore, about the melting point of magnesium oxide, which has 2 plus ions and 2 minus ions, when compared with, for example, sodium fluoride, which has ions of a similar size, but each is only 1 plus and 1 minus? Let's have a look at the melting points. As you can see, the melting point for magnesium oxide is substantially larger because of that extra pull from the 2 plus ions attracting the 2 minus ions. Now think about calcium oxide and beryllium oxide. They both have plus 2 and 2 minus ions, and all we've done is change the metal ion from magnesium to the larger calcium ion. The charge is just as strong, and if we make our ions even larger, what will that mean for how strongly they're able to attract to all their surrounding ions? Well, in this case, the magnesium oxide actually has a higher melting point than the calcium oxide. When we have the same charge but in a larger volume, we say that the charge density has decreased. Ions with a high charge density are able to attract each other very strongly because they have a high charge and can get very close to each other. This way of imagining bonding in ionic compounds is called the Ionic model. By treating the particles as hard, charged spheres, a little like those magnetic toys, we're able to predict the properties of these materials very successfully. This is a sign of a good model. The model is not perfect though. For one thing, we understand that in reality, particles this small are in actual fact anything but hard spheres. They tend to be more fuzzy in their nature, so don't get too attached to this mental image. Just understand that it can be a useful one for explaining a lot of the behaviour of ionic compounds. For some materials, the numbers predicted by the ionic model don't accurately match up with the true measured values. It's one reason I didn't compare beryllium oxide with magnesium oxide above. The numbers don't quite behave in the way that the model would predict. This means that we have to adopt a more nuanced model that allows for the fuzziness and flexibility of these spheres, and this will be the subject of a future video. So, in summary, properties of ionic compounds tend to be brittle, they tend to be soluble in water, they tend also to have high melting and boiling points, because of these strong forces of attraction between all of the positive and negative ions, and they conduct electricity only when they're molten or dissolved in solution. We can explain these properties by using the Ionic model, one in which we imagine that the particles are behaving as hard spheres with opposite charges, and they arrange themselves so that they're surrounded by ions of the opposite charge, to which they're attracted very strongly with an electrostatic attraction.